All right, so for the mean value theorem, section 4.2, the theorem states if y equals f of x is continuous at every point on a closed interval and differentiable. Okay, so this is where the differentiability comes in. Remember, the EVT did not have differentiable at every point of its interior from A to B, so it doesn't have to be differentiable on the endpoints. There is at least one point C in the interior points at which f prime of C is equal to f of B minus f of A over B minus A. This is also known as the existence formula. The question being, does C exist? All right, so if any part of this is not true, then the mean value theorem is not true. So if it's not continuous and it's not on a closed interval and it's not differentiable, then we cannot use the mean value theorem. So the graphical representation, this is what we're looking at. So the idea is from A to B, if we have a function from A to B, and let's call this point right here C. The idea is that the slope of this line, so that secant line, so the slope, which is f of B minus f of A over B minus A, so the slope of the line from the first endpoint to the second endpoint will be equal to the derivative of the function at C. Okay, so the slope of the tangent line. So the slope of the secant line will be equal to the slope of the tangent line at some point called C. Okay? So these two, the slopes will be equal because they are parallel. So the lines are parallel, which makes the slopes equal. All right? So there's a few different representations of what this is saying. Oh, and let's call this f prime of C right here. So that's the slope f prime of C. All right, so there is verbal physical interpretation of the mean value theorem. First of all, we used the mean value theorem when we were finding the average rate of change. So average rate of change, which is basically the slope of the secant line, right? F of B minus f of A over B minus A from A to B. And that will equal f of C. There's the instantaneous change, which means take the derivative of C. So take the derivative of all of this. And then there's the mean value theorem, which says that f prime of C at some interior point, so the slope at some interior point must equal f of B minus f of A over B minus A over the entire interval. Okay, so that's what the mean value theorem says. There's two different parts of the mean value theorem. There's the average rate of change, and then there's the instantaneous change. So for example, if a car takes 8 seconds to go 352 feet, we know that its average velocity is 352 over 8, right? 352 feet over 8 seconds, which equals 44 feet per second. Okay, or if we convert that to miles per hour, 30 miles per hour, just so that it makes sense in our heads because that's what we're used to. So what the MVT says about this statement right here at some point during those 8 seconds, the speedometer read exactly 30 miles per hour. Because remember, we talked about this, right? Just because you're going an average velocity of 30 miles per hour doesn't mean that you're going 30 miles per hour from beginning to end. It just means, you know, you're approximately around 30 miles per hour. But what the MVT says is that somewhere in between, we did get a reading of 30 miles per hour. So let's do a few examples. Show that the function f of x equals x to the 2/3 satisfies the mean value theorem on the interval 0 to 1. Then find the solution C to the MVT equation on this interval. So the question is this continuous? Is it differentiable on the interval? And is it on a closed interval? So it is on a closed interval. X to the 2/3 is continuous. I can plug in any number here, basically plug in 0 to 1, and I will get an output. And if you looked at the graph, you can look at the graph a little bit later, but we can look at the graph. I'm just going to graph it really quick. So x raised to the 2 divided by 3. There it is. Remember, I just care about 0 to 1. Okay, and it doesn't have to be differentiable at 0. It just has to be differentiable in between 0 and 1. And it is differentiable and it is continuous in between the intervals. So the question starts being, is f prime of c equal to f of b minus f of a? Now, because these three things were checked off, this should be correct. So f prime of c equals f of 1 minus f of 0 over 1 minus 0. So f prime of c equals 0. Okay, so since all these are correct, then this must be correct. So right now we found f prime of c to be 0, but we need to find the solution of c. Okay, and in order to do that, we need to first find what is f prime of x. So f prime of x is going to be 2/3 x to the negative 1/3. Alright, now f prime of c and f prime of x, that's basically the same exact thing. I'll explain this a little bit more when we're doing the homework problems. So I'm going to rewrite this as 2 over 3 square root of x cubed root, and I'm going to call this, instead of f prime of x, it's f prime of c. There's no difference here, okay? When we say f prime of c, we're focusing on a point that is on this derivative. So I'm trying to figure out what c is, or what that x is. So I'm going to set this equal to 0. And once you solve it, it means multiply both sides by 3, divide by 2, multiply by by 3/2 on both sides to cancel out the, I don't have the space, but you multiply by 3/2 to cancel out the 2/3, and you're left with you're left with 0 equals 1 over the cube root of c, right? Because we're just solving for our x or a c. You can call it whatever you want. It doesn't really matter. It ends up being the same thing. All right, so once you solve this, I just made a mistake here. Sorry, guys. So this is f of 1 minus f of 0 over 1 minus 0, which is 1. Right? Because f of 1 is going to be 1 minus 0 over 1 minus 0, and that's 1. So we're going to set this equal to 1. Okay? So this is equal to 1. Sorry. All right, and then you multiply both sides by the cube root of c, so you get cube root of c equals, or x, okay? I know I keep going back between x and c. I just need you guys to understand that at this point, x and c are the same thing. Take the cube both sides, so c equals 1. So we proved that it works with these 3 being checked off, and then we were able to use the MDT to find what c is. All right, show that the function f of x, absolute value of x, does not satisfy the mean value theorem on the interval -1 to 1. Explain graphically. So if we look at the graph of the absolute value function, the question becomes from -1 to 1. So the question becomes, is this continuous? Yes. Is it on a closed interval? Yes. Now, is it differentiable everywhere? No. Why is it, where is it not differentiable? At this corner right there. Okay? Hey. Yeah. No. But I did save them if you wanted them. Yeah, they're inside that basket. Cool. You can actually use them. Yeah, and there's more in that other basket. Sorry. All right. Okie dokie.
These won't actually touch the ice cream samples. Ice cream can go in here and then you put it in another bag.
Yeah, makes sense.
So ice cream stays
So
clean.
it stays clean, yeah. So because this does not work, sorry for the interruption. You guys can, I'm sure you fast forwarded through that. So because these 3 things don't match up, then we know that f prime of c does not equal f of b minus f of a over b minus a. So the mean value theorem should not work. So the idea becomes, let's see, f prime of c, f of 1 minus f of -1 over 1 minus -1. So f prime of c is going to equal 0 when you do this. Okay? And then we can check what is actually f prime of c. So f prime of c, which is just the absolute value of of x, what is the derivative? I know I keep confusing you guys with the c. Alright, what is the derivative of this? So f prime of x of this is just going to be 1. Okay, right off the bat, you see that. And look, what do you notice? That f prime of c based on this is 0, but the actual f prime of x, or c, whatever you want to call it, is 1. Okay, so we're running into 15 minutes. Let's leave this problem. We'll do it when I get back on Thursday. And then we will talk about this when I get back on Thursday. Okay, so you're going to do part 1 and part 2 right after this.